mentioned Goose services several times in this presentation. Now we'll come to define how the protocol works, how the models work, and the services. Goose, Generic Object-Oriented Substation Event, came about really in the early days of UCA. We needed a way to model basically tripping and breaker relay communications, which is typically done with a fixed hard wire. We wanted to be able to simulate that or emulate that kind of a system over the LAN with some reliable distribution of data from a single source to multiple subscribed peers. So it's a subscriber-publisher model. We needed to get high reliability in that kind of a scheme, but we wanted it over the LAN. I'll talk a little bit more about how the protocol works and how we actually implement that to get that reliability. But to start with, Goose is arbitrary data. The generic substation state event, which was the original UCA mechanism that was defined, works with the same mechanism, but it sends a fixed set of status bits. There's no data set involved, and the bits are somewhat defined by between publisher and subscriber. But it also uses the fast, reliable multicast capability. From a data point of view, we have our similar to reporting model. We have data objects within a data set that are generating a series of change events. These are formatted based on settings in a Goose control block, which is controlled by the client. And the difference is the messages always send the entire data set. They are fast multicast reports, and I'll talk about how that multicast works to get the reliability that we were after. Multicast is a problem in any protocol. When you have that kind of requirement, there's some inherent reliability. They're typically unconfirmed. In our case, it was particularly impractical to use a confirmed service. We needed to have trip times and switch closure times in less than 4 milliseconds was our target requirement. And if you think about it, using most protocols, if you were going to do confirmation, then by the time you wait for the confirmation to come back from the receiver, it's too late to resend because you're already outside your 4 millisecond window. This is particularly a problem when you've got multiple subscribers coming to a single publisher, being able to resolve all of that. So instead, after some work within the UCA community, we came up with the idea of being essentially pessimistic. We assume that the subscribers didn't receive the data, and we go ahead and retransmit it as if they had not received it. When the data is stable, basically we retransmit very quickly to be able to get the times that to meet the timing requirements that we had. As the data gets more stable, so you're farther away from a change event, then the retransmission rate spreads out so we don't overload the LAN. And basically then it comes to some fixed rate which subscribers can use to detect loss of connection, and new subscribers that come on after the change event will still get the current data. This retransmission policy is shown in this diagram. The red bars are the messages that represent the real change. That's when new data has occurred. Something has occurred in the process logic that caused the data to change. The message is sent containing the entire data set, and then there's a fast retransmission that occurs, which gradually, over some kind of a strategy, spreads out so that we're not burdening the network. Each message contains the time interval to expect the next transmission, so that you can tell if a message is dropped, you know that you've lost connectivity with the publisher. The second red bar then is the second change event. We will then start the retransmission policy all over again doing fast retransmissions until we reach some fixed amount. So each message contains the time to wait for the next message, and so you detect dropouts. And the maximum retransmission rate is configured to be the time that is acceptable for new subscribers to get the data. The messages that are defined in the Goose link layer protocol are multicast link layer packets. That means in our case it's VLAN packets on the Ethernet, Each packet contains identification data, basically the name of the Goose control block, the data set, and some other identification of the source of the data, or the publisher. They all contain a data set name, configuration ID, and the values of the members of the data set. I mentioned these extra services. There's a service where a subscriber can essentially request back to the publisher to ask for the definition of the data set, to be able to resolve the data set members to make sure that their configurations between publisher and subscriber are the same. As I said before, each message also contains the time to the next retransmission for being able to maintain the connectivity and know when you've lost a connection. They each contain a test mode bit so that we can do test Goose messages to be able to do in-circuit testing of devices over the LAN. And they also contain a security parameter, which basically contains information to validate the source of the data. 61850 Part 8.1, which is the only current implementation of Goose, the only SCSM that builds out Goose, uses VLAN over Ethernet. So that allows us to run over the Ethernet but still maintain another level of reliability, because you can basically reserve the bandwidth in the routers and make it higher priority. The GSSE model, as I said before, is almost exactly the same as the Goose model, except for that it's sending a fixed set of status bits instead of an arbitrary data set. This was the original UCA Goose, and it's been carried forward into 61850, but the model was extended in 61850 to do the full Goose with an arbitrary data set, arbitrary data. The sampled values model is similar to the Goose in that it's built out in Part 9-2 as another link layer protocol that coexists on the VLAN Ethernet. It's used at the process level to send synchronized samples, typically from current transducers or voltage transducers, that sort of thing. It's used at the Bay unit level for synchrocheck. One of the issues about multicast in this VLAN Ethernet is that it can only really be used within one local network segment. Those multicast packets at VLAN aren't passed through routers. It's not a routable protocol. So the sampled values model includes a way of basically running them through a TCP pipe so that you can get a connection to a sampled values publisher across the network and be able to get the samples directly in a TCP directed connection. The iconic model looks very much the same as the Goose model, except for that we're using arbitrary data and it's not event-driven, it's sampled. Now, these samples can get combined in various ways into the periodic reports that go out on the Ethernet, again, controlled by a control block and formatted according to various rules.